Hello, everyone. This is the lecture for section 2.2 and 2.5, the limit of a function. So the first thing that we have to get into in studying calculus is this idea of a limit, okay? Hopefully you've heard about it from pre-calculus. In this section and in the beginning part of this class, we're gonna build up an intuitive definition, and then at the very end, we'll finally get to a really, really nice the mathematical robust definition for a limit, okay? So what I want to do first is I kind of want to start with an example to show you guys what I'm talking about, okay? What we're going to do first is we're going to consider a function. We're going to consider this function right here, okay? And I'm going to walk you guys through the analysis of this, okay? X squared minus 16 all divided by x minus 4. So the first thing that we're going to find is the domain. And hopefully you guys remember, right? The domain of this function, make that a little thinner, there we go, is, the domain of this function is negative infinity to 4 union 4 to infinity, okay? And the reason why we have to kick out 4 is because of this right here. It's because of that bottom, okay? If we plug in 4, we're dividing by 0, right? We can't have that. So we have to remove 4 from our choices, right? So that leaves everything else, okay? That answers A. So we see that there's going to be a problem when we get closer to 4, right? So what I want to do is I'm going to use a graphing utility, and I want to see what's going to happen as we get closer to 4, okay? So what I'm going to do is I'm going to bring in Desmos. I'm going to split my screen now, okay? And I've already got the two for examples that are coming up here, okay? So let me graph, put that there. Here is the graph for f of x, okay? Now, remember how I said there's going to be a problem as we approach 4. So if we get closer and closer to 4, notice what happens. It says that it's undefined, right? But I can analyze what's happening as we get closer to it. So the way that I'm going to do that is I am going to choose values that get closer and closer to 4. So this is going to be that value 4 that we can't plug in, right? So what I'm going to do is I'm going to choose 3.6, 3.7, 3.8, 3.5, 3.6, 3.7, 3.8, and 3.9, okay? So what I want to show you guys is how Desmos does the computation for you. I'm going to go ahead and insert a table here. I'm going to get rid of the subscript 1, and I'm going to get rid of the y. I'm going to put in f of x. Okay, and I'm going to change this one to g of x. So now I'm telling it to compute stuff for f of x, right? So 3.5, 3.6, 3.7, 3.8, 3.9. So it is computing things for me here, if you guys see that, okay? And here's my table. So the f of x values for 3.5 is 7.5, right? And it goes 7.6, 7.7, 7.8, and 7.9, okay? Cool. Let's do from the other end. So from the other end, I am going to, come on. I'm going to go 4.1, 4.2, 4.3, 4.4, and then 4.5, okay? And again, I'm going to go ahead and just have Desmos compute stuff out for you, because it can do that. 4.1, 4.2, 4.3, 4.4, 4.5, okay? And you guys see, this is going to be 8.1, 8.2, 8.3, 8.4, 8.5. So now I'm going to get rid of my double screen here. I'm going to bring this front and center again. My computer likes to be buggy sometimes. I'm sorry. There we go. Oh, come on. There we go. All right, that's good enough. Okay. So what I want everybody to see is this. On the top row, right, my X values are getting closer and closer to 4, right? What I want to do is look at what's happening to my bottom values, my f of x values. And if you guys see, my f of x values are heading toward, hopefully you guys see this, it's heading toward the number 8, right? So what we say is that my f of x values are tending toward the value, oh, wrong 8, there we go, okay? So my f of x values are getting closer to the value 8 as my x values get closer to 4. Okay, and this makes sense if we jump back to our Desmos graph. Let me put that one front and center. There we go. You guys can see, turn the dots off. As I approach 4 on my x values, right? My y values say it's undefined, right? But they're really heading toward the value 8. Okay? All right. That's the end of example 1. Let's move on to example 2. So, same idea. Okay? If you guys take a look, the domain for this function is negative infinity to 0, union 0 to infinity. We have to leave out, for this function right here, we have to leave out 0 because I get to divide by 0 if I plug it into that thing. We can't have that, okay? Again, I'm going to do the same thing. So I know I can't plug in 0, but I'm going to analyze what's happening as I tend toward it, right? So from the top end, I'm going to go ahead and do 0.1, 0.2, 0.3, 0.4, 0.5, okay? And then from the left end, I'm going to do negative 0.5, negative 0.4, negative 0.3, negative 0.2, negative 0.1, okay? Okay. I'm going to go ahead and throw this all into Desmos again, okay? So I'm going to turn the original one off. I'm going to turn the other one on, and I'm going to put that one front and center. There is the function, okay? You guys see how it splits, right? Okay, I don't need the values to be computed for f of x now. I'm going to change this to g of x. And I'm going to change my x values now. Okay, so what I'm going to do, I'm going to do the split screen thing again. Bam, there we go. Okay, I'm going to do negative 0.5, negative 0.4, negative 0.3, negative 0.2, negative 0.1. Okay, so we have some x values here. Okay, our x values are, or sorry, our y values are 0.88, 0.92, 0.96, 0.99, 0.999. All right, so now let's do the other end. Okay, and I want to do the same thing. I'm going to compute everything. 0.1, 0.2, 0.3, 0.4, 0.5. Okay, this is going to be something very small. 0.0000453. 0.2 is going to be 0.000001. 0.669. 0.3 is going to be 0.03. 0.4, 0.07, and then 0.5, 0.119. Okay? Okay. Let's move this all back together. There we go. So, doing the same thing as before, right? Notice that my top row is heading towards 0 from both ends, right? But what I'm curious about is what my bottom row, what my f of x values are doing in this case, right? And those are really weird, okay? So on the left-hand side, so if we take a look at this side over here, okay? On the left-hand side, those values look like they're getting closer to 1, okay? As opposed to this other side, right? Those values look like they're getting closer to 0, okay? So the actual value here does not exist. So what we say here is that the limit does not exist. So this is different. Does not exist. This is different from our first example. Notice that in our first example, our x values headed toward 4, our y values from both ends were heading toward 8, right? Okay. In this second example, our x values were heading toward 0, right? But our y values, our f of x values, were not heading toward a particular value. Okay, so in the first example, right, they headed toward a value, we say that the limit is 8. Okay. In our second example, since it wasn't heading toward a specific value, we say that the limit does not exist. Okay, which brings us to our very first definition. Okay, this one's got a picture attached to it. Okay, I'm going to read out the definition, and I'm going to draw the picture that it sort of describes. Okay, if f of x is a function and the values of f of x get arbitrarily close to a number L, as x gets sufficiently close to a, then we say that the limit of f of x as x approaches a is equal to L, and we denote it this way. This is the calculus way of us writing that a limit of a function is equal to L. Okay, so the picture that goes along with it is basically what we were doing just now. So I'm going to draw my x and my y axis. Okay, this is my y axis, this is my x axis, right? I'm going to draw a nice function. So suppose this is my f of x, right? And I want to approach this value right here. And this is going to be my a value. Okay, we say that the limit as x approaches a of a function f of x is equal to L if we do this. So if we're coming at it from the positive end, right, and we come at it from the negative end, it should be approaching a specific value, and whatever that value is. So I'm going to draw another dotted line here. Whatever that value is L. You guys see how it's sort of approaching, right? So what we did above is the numerical analysis for a limit. Okay. Okay. So the next thing that I want to try is this. I have some quick checks for you guys to try. Please make sure you do them. You're only responsible for the one that's for your group. Okay, so if you're group 1, you only have to do the first one. If you're group 3, you do that second one. Okay, so on and so forth. You don't have to do them all. Just do the one that is assigned to you. Okay, so take a couple minutes, try this out, use Desmos, fill in the table, and converse with your group mates. Okay, moving on. So now that we have an intuitive definition of what a limit is supposed to be doing, okay, we're going to refine a little bit more that definition, okay? And that definition is this right here. They look the same as what I've been writing up above, with the exception of that. One of them has a little plus as an exponent, and the other one has a little negative as an exponent, okay? And these are what we call the left-hand and right-handed limits, okay? So let me scroll back, okay, to our original examples. When we were doing this side, right? When we were doing this side over here, this was the limit as x approaches a from the positive side. Okay, and we were doing this side over here, right? We were saying that the limit as x approaches a from the negative side. Okay, that's the difference. So we basically broke down our definition of a limit to a left-handed, a positive limit, or a right-handed, the negative limit. Okay. This brings us to the next theorem, okay, that the limit of a function exists if and only if both the left-hand limit exists and the right-hand limit exists, and if they are equal, then that is going to be the flat-out limit. So the best way for me to write this out, I think, is this. So the limit as x approaches a from the positive side of f of x has to equal the limit as x approaches a from the negative side of f of x. And this is equal to the limit as x approaches a of f of x. I like to call this one the flat limit, though, because it doesn't have the plus or minus on it. Okay, so if these two exist, then it must be equal to the flat limit, the one without the positive or the negative. Okay, so let's go ahead and practice this. I've got an example here, okay? And we're gonna see what's gonna happen with each one of these, okay? So let's do this first column right here, okay? The limit as x approaches -3 from the positive side. So what I'm doing there is I am trying to approach x equal -3 from the positive side. So I'm doing dot, 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 dot like this, right? Okay. And if you guys can see, that looks like maybe 2.5. So I'm going to call it that. So 2.5. The y values for g of x as I approach -3 from the positive side is about 2.5. Okay, cool. Okay, next one. The limit as x approaches -3 from the negative side. So now I'm still approaching, right, -3, but now I'm doing it from the left-hand side, right, from the negative side. And if you do that, let me actually thicken up my dots for the red. You guys see, those y values are getting closer to this right here. So this answer is actually going to be -4. Okay, so now we get to use the theorem that we have up above, that the limit exists of a function exists if and only if the positive limit and the negative limit match them. Okay, since the top limit, since the positive limit is 2.5 and the negative limit is -4, this does not exist. And it turns out my function in and of itself does not exist either. If you guys take a look at the graph, right, both are open circles, right? So it's not defined at -3. Okay, moving on. Let's try this again. We're going to do f of x, sorry, limit as x approaches 2 from the positive side of g of x. Okay, so I'm trying to approach this x value from the positive side. So, dot, dot, dot. It looks like my y values are heading toward 1. Okay, same thing from this side. So the limit as x approaches 2 from the negative side. Dot, 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 dot. Same thing, my y values are approaching 1. Since both of those limits are equal, the flat limit has to be equal as well. Got it? Now, if we take a look at g of 2, right, that does not exist. So the function is not defined at that point, but the limits do exist. So the function is not defined at that point, but the function values before and after are heading towards something. Got it? Okay. Last example. The limit as x approaches 0 from the positive side. Okay, so we want to approach 0. We want to approach the origin, right? From the positive side. So, dot, 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 dot. Those y values look like they're going toward 2, right? From the negative side, dot, 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 right? If we want to do from the negative side, those values also look like they're going toward 2, okay? Since both the positive limit and the negative limit are equal, that limit is good old 2, okay? And in this case, our function, g of 0, is actually defined. There's no open circle there. That is actually 2, okay? So this is sort of, we're still getting the intuitive definition of a limit still, okay? Hopefully this helps out a little bit, okay? Moving on, now that we have the intuitive definition of a limit that head toward a point, right? We now can describe these two, okay? If a limit as x approaches a either positive or negative, right, goes to positive infinity, or the limit as x approaches a, either the positive or the negative limit, goes to negative infinity. So both of those, right, is exactly how you think, right? As our x values approach a value a, right, we say that the limit is positive infinity if the f of x or the y values increase without bounds. They just keep growing and growing and growing and growing, okay? And vice versa, if the y values just decrease without bounds. So if they just take a nosedive, right, then we say that that limit is negative infinity. Okay. For this definition, the same thing works out. So if both the left-hand limit and the right-hand limit go to positive infinity, then we say that the flat limit also goes to positive infinity, right? And if both the left and right-handed limits go to negative infinity, right, then we say that the flat limit goes to negative infinity as well. So the same thing sort of works out, okay? All right, so an example of what I'm talking about. Okay, so we have this function right here. It's a little bit of a pop quiz from pre-calc. You guys should be able to recognize that this function has two asymptotes. One asymptote at 2, so I'm going to draw in that asymptote right there, okay, positive 2, and another asymptote at x equal 3. So I'm going to plop down that one too. So it's got one vertical and one horizontal asymptote. And the graph for this thing looks something like this. It's a double swoosh. You guys remember, so it's a whoosh and a whoosh. Okay, so we see that 3 is going to be x equal 3, right, is going to be some sort of a problem. So that's what we're going to be looking at, okay? So let's take a look at the first one. X approaches 3 from the positive side of f of x. So I want to approach this x value, right? I want to approach this x value from the positive side. So I am going to use the green highlighter. As I start going that way, right, I'm approaching 3. My y values are increasing without bound, right? So that means that this limit is going to be positive infinity, okay? Doing it from the other end, so let's take a look at this limit, okay? The limit as x approaches 3 from the negative side, so I'm going to do the exact same thing, except I'm going to be doing this now, right? You guys see how my x values are approaching positive 3. I'm looking at the y values, and those are taking a nosedive, right? So this is going to be negative infinity, okay? So since both of these don't match, right, we get to say that this limit does not exist. Both of the limits had to be equal. Both of these had to be equal in order for that flat limit to exist. Since they don't, we have a limit that does not exist. Okay, next example. This one's one of the lesser known functions, okay? You guys remember this one? If not, that's all right. You can throw it into Desmos and it'll give you a graph for it. Okay, so the graph for this one looks similar. Okay, there's going to be a horizontal asymptote at positive 3. And there's going to be a vertical asymptote, one that goes up and down, at positive 3 as well. Okay, the graph of this, notice that it's a -1, right? The graph of this is going to be a double swoosh, but the swooshes go in the same direction. And they're going to go in the negative direction. So it's actually going to look like this. It's going to whoosh down, whoosh down. Okay? So let's do this first one. The limit as x approaches 3 from the positive side. Okay? So again, I'm going to do the same thing. I'm going to whoosh this way, right? Hopefully you guys see that the limit for this one is negative infinity. Okay, and if I do the exact same thing from the other end, right, that is also negative infinity, right? These now do match. So that means that the flat limit, the one without the positive or the negative, has got to be negative infinity. Okay. Now, this brings up a sort of a misnomer in terms of a calculus. By the limit definition, any limit that goes to positive or negative infinity, they do not exist because they need to approach a value, right? Positive and negative infinity aren't values, they're directions, okay? So when we write this is sort of an unspoken rule, an unwritten rule. When we write something like this, it's to describe a function's behavior. This is the best thing that we've got in order to describe a function's behavior. Just keep that in mind, just in case, so it doesn't confuse you with sort of like the bona fide definition of a limit. Okay. Next definition that I've got for you guys is that of a vertical asymptote. So hopefully you guys remember in pre-calc that a vertical asymptote is supposed to be a line that a function either it gets really close to it, but it doesn't cross it or it doesn't touch it, right? But sometimes, if you guys remember in pre-calc, you had functions that did cross the vertical, or sorry, not the vertical, the horizontal asymptote, right? And you probably ask yourself, well, it crossed the horizontal asymptote. What gives, right? It's because we didn't have the proper notation, the proper definitions to describe what an asymptote is, okay? And now we do. A vertical asymptote is when anything like this happens, where in the long run, the limit as x approaches a, either the positive or the negative, head toward positive or negative infinity. So basically, it's either one of these functions, the one right above it, or an example like we had in example 4. Okay, this is the bona fide definition of a vertical asymptote. if the limit from the positive or negative side or the flat limit go either to positive or negative infinity. Okay, cool, cool. Moving on, I got some stuff for you guys to practice here. Try these out again. Do these with your classmates, with your group mates. Use Desmos for all of these, okay? Provide your solution in the group discussions, and I'll pick out a couple to put in our notes, okay? Moving on so now that we have a very good working definition, a very good intuitive definition for what a limit is, okay? I'm going to now cover the precise definition of a limit, okay? And I've got to warn everybody for this. This computation is very, very, very mathematical, okay? As a matter of fact, a lot of you, unless you are going to be studying math for the rest of your life, will not need this. However, I do need to describe it as part of the course, okay? The picture for it is very intuitive. Everything is very intuitive for it, but the description, the definition overall is very, very difficult to grasp. Okay, so let me read it out, okay, and I'm going to show you guys an example, okay? So the precise definition of a limit, okay? Suppose you have f of x, and it's defined for all x values, but not at a, over an interval containing a, okay? And let L be a real number. Then we say that the limit as x approaches a of f of x is equal to L if for every epsilon greater than 0, there exists a delta greater than 0, such that if my x minus a is less than a delta, right, then my f of x minus L is less than epsilon. Okay, here we go. Hopefully this makes sense, okay? So I'm going to draw the picture for it. This is my x values. These are my y values, okay? I'm going to draw a function here. There's my function, okay? And suppose I want to approach my value a, okay? So I'm trying to approach at this point right here. All right, here we go, okay? What this thing is saying is that, first of all, let me get rid of the highlights. And I'm going to go through the highlighted portions once more in steps, okay? For every epsilon greater than 0, there exists a delta greater than 0, okay? What this basically is saying, what these two portions are saying, let me put them in blue. What these two portions are saying is that I can contain my outputs, right, based on a containment of my inputs. Okay, so what we're saying is this, that I can go, let me choose this. A delta, oops, this is plus, this one's minus. So what I have here is this, x minus delta, x plus delta. Whoops, a plus delta, a minus delta. So I'm going to go ahead and draw this right here. Okay, it's saying that I can contain my x values, okay, and containing my x values should produce a containment in my y values. So I'm going to draw this. There we go. So I'm going to choose this right here. This is my L. And I'm going to do plus epsilon minus epsilon. So this is going to be L plus epsilon. And this right here is going to be L minus epsilon. Okay. So basically what this thing is saying, let me go through this one more time. Okay. That for every epsilon bigger than 0, so for every containment, for every containment in my y values, okay, for every containment in my y values, I should be able to choose a delta, right, that contains my x values such that my y values are contained as such. Okay. Like I said, most of you will not need this unless you're going to study math for the rest of your life. I've got it covered as part of the course. Okay. So let me give you guys an example of how this thing works out. Okay. So this is the actual bona fide definition, how to prove the limit of a function as x approaches a value. Okay. So in this case, in particular, I'm going to prove that the limit as x approaches 4 of the square root of x is equal to 2. Okay, I've got a QR code there. If you guys have your phone out, you can go ahead and scan it, and it'll pop up this thing right here. Let me show you guys what I'm going to be working with. It's going to pop up this thing. Okay, this is sort of like an explanation of what the epsilon delta definition of a limit. Okay, so what I want to do is, first of all, I have to go ahead and show you guys the computation that's involved with this. Okay, so the idea behind this is I want this to be true no matter what. X minus 2, right, has to be less than epsilon. Okay, and my goal in life, right, whenever I prove these, is I want to find this delta. I want to find that delta. Okay, so the way that these usually work is we usually start out with this line. We usually start off with this portion right here, and then we try to find a delta that satisfies it. Okay, and then I'm going to go ahead and do the proof outright. Okay, so if this is true, so let's start with this. If this is true, then we have this. X minus 2 is less than epsilon, and that's got to be bigger than a negative epsilon. Okay? That's what the absolute value means, right? So plus 2, plus 2, plus 2, minus epsilon plus 2, square root of x, epsilon plus 2. Okay, we're getting there. We're getting there. In order for me to get rid of that square root, I need to square plus 2 squared x epsilon plus 2 squared. Okay, so now I want to get this. I want in here, in this middle portion. Let me highlight it. Let me highlight it in purple. In this middle portion right here, I need to get something that looks like x minus 4. So if you take a look at the definition of a limit, this is the thing. Whoa. This is the thing that we're looking for, right? So we need to get something that looks like x minus 4. In our case, our a is 2, right? So the last thing that's left, right, is if I subtract 4 from all of my inequalities, I get left with this. Whoops. Minus epsilon plus 2 squared minus 4 less than x minus 4 epsilon plus 2 squared minus 4. Okay, so now this right here, this statement right here, looks like what we did at the beginning. Okay, so we've sort of found our epsilon, or our delta here. Minus epsilon plus 2 squared minus 4, epsilon plus 2 squared minus 4. Both of these values might be different. So remember, we have one of them is a positive epsilon, the other one's a negative epsilon, correct? Okay. Since it's two values, right, what we're going to do is choose the smallest of the two. It doesn't matter which one, but we have it rounded down to one of these two. It's either this one or this one. Okay, so now this is how I like to explain it. Okay. Okay. So now that we have the work, the way that I like to describe this is this way. So when we go downward, right, when we do this kind of idea, right, this is going to be the work. This is kind of like the work that we need to do in order to sort of get all our ducks in a row, okay? And when we go the opposite direction, when we go this way, let me actually make that thicker. When we actually go this way, whoops, the other way. This is the proof. So the appropriate way to prove the limit, okay, is actually the opposite direction of the work that we just did. So to prove it, whoa, proof. Whoops, let epsilon be bigger than 0. So we let epsilon be bigger than 0 and let our delta be equal to the minimum, right, of those two values. Minus epsilon plus 2 squared minus 4, and the epsilon plus 2 squared minus 4. Okay? So then the work now goes backwards. So we have to just show this now, right? So we have to show that x, whoops, without the bar, x minus 4 has to be less than positive delta and negative delta, okay, which is smaller than these two values. It's going to be smaller than on the top side, right? Epsilon plus 2 squared minus 4, and it's going to be smaller than this right here, minus epsilon plus 2 squared minus 4. Okay, like I said, now the work all goes backwards. Okay, so then that means that my minus 4s go away. So minus 4 on everything makes those go away. So then minus epsilon plus 2 squared has to be less than x less than epsilon plus 2 squared. Okay. To get rid of the square root, so minus epsilon plus 2, and then I have to square root the middle one. Okay. To get rid of my plus 2's, minus 2, which means I need to minus 2 in the middle. So minus epsilon is less than the square root of x minus 2 less than epsilon. And this is the thing that we wanted to begin with, right? The square root of x minus 2 is less than epsilon. So the idea, right, is that we let epsilon be bigger than 0. okay? And if we let delta be the minimum of these two, right? Then we have a containment of our x values, right? That produces a containment in our y values. Okay, now, let me go to the Desmos thing to show you guys what that means. Okay, so here's our Desmos graph, okay? I'm going to grab my point and I'm going to move it toward x equal 4. Okay, I'm going to zoom in there. Okay, and what I want to do is, hopefully you guys see on the left-hand side, there's two options for you that changes your epsilon and your delta. Okay, so I can grab my epsilon, make it as big or as small as I want, right? Okay, and I want you guys to see, let's go ahead and make it 0.2. There we go. Okay, if I make my epsilon 0.2, right, I need to make a delta that is small enough, so my my horizontal sort of box, right? I need to make that small enough, right, so that it contains my outputs, right? And if I make that too big, you guys see what happens. If I make it too big, my y values aren't contained. You guys see that? This one actually extends way too far. It's not inside the blue box, right? There's gotta be a value somewhere really close. You guys see those points? There it is, right there. And it changes to green when the delta is small enough. You guys see that? So if my epsilon is 0.2, if my output boundaries, right, are 0.2 away, right, then my delta boundaries has to be about 0.763. Okay, so if I can contain my outputs, my y outputs, right, there exists a delta that contains my inputs. Okay, all right. Like I said, this kind of work is really not going to be required for a large majority of you, unless you're going to be studying math for the rest of your life, but I do have to cover it as part of the course, okay? If there's any questions on any of this stuff, please come to my office hours. Send me an email or visit during my online office hours as well, okay? Or in the tutoring lab on campus, okay? After this is lecture questions, so go ahead and finish these up. If you have any questions, again, come visit me, and I'll see you guys around.